Hi class, now we're going to volumes, and volumes look spooky, but really they're not. And we've actually gone through this briefly in class. There was no formal discussion about it. I was just showing you as a matter of curiosity how volumes work with integration. And they're not hard. All you need to remember is the formula for the volume of a cylinder. That's all you need to remember. Now, if we go back to looking at a cylinder, I'm going to have this cylinder lying down horizontally for a good reason, okay? But if we have a cylinder lying down horizontally like that, then this, in cylinder dimensions, that's called the height. And of course this is the radius, so we'll just call that R. We've got the radius. And to find the volume of a cylinder, it's the area of this circle times the height. It's kind of like a formula for a prism, but that's the formula for a volume. So it's the volume of a cylinder is equal to the area of the circle, which is pi r squared, times the height, which is h. Now you'll see why that is so important with what we're going to do over here. Let's just say we've got some function. Again, I don't know what the function is, and I don't really care, mostly. There's just a function here, okay? There's a function there. Now, we know how to find the area underneath this function, but what I want to do is I want to take a chunk of this function here, which to date has just, we've found the area of that. But I want to take this portion of the function and I want to rotate the whole function around the x-axis. So we're going to have like well, it's not going to be a cylinder. This would end up looking somewhat like the horn end of a trumpet, how it blows out like that. It would look something like that. If I took this shape and rotated it around the x-axis, we would have this kind of horn-shaped thing here that goes like that. And you know what? This thing here that I've got to do with area, that's now confusing, so let's get rid of that. We don't want that anymore. Okay, so we've got this horn sort of shape that's rotated around, or this curve which is rotated around the x-axis. Looking at the cylinder, this h is equivalent to measurements along the x-axis, and the terminology we use is dx. What we're really doing is we're taking this bell shape that looks like that, we're taking the bell shape and we're actually going to make little cylinders all of dx units long. They're just tiny little cylinders. And if I did just 2 or 3 cylinders, it would be a really rough approximation to the shape of the volume of this curve, or this rotation. But if I took 100 cylinders, then the approximation to the volume would become much better. It'd be much better. If I took 1,000, it'd be getting much, much closer. And if I make the h value here smaller and smaller and smaller, until it's infinitesimally small, then what we end up with is the exact volume of the rotation of this curve around the x-axis. So this dx represents the limiting sum of if x is made if h is made infinitesimally small, then that's what the dx is telling us. And of course, we discussed earlier that the integral sign is actually just a simplification of summing all the bits and pieces. So we're summing all the bits and pieces as dx, or as h, gets infinitesimally small, which means that we'll end up with dx. So I'll just get rid of my little scribbles here. Now, so h is equivalent to dx, and then if we look at this cylinder here, the radius, this dimension from the centre out to the edge of the cylinder, well, the centre line is actually equivalent to the x-axis again, And in this scenario, the radius is actually given by, at that point, the radius is given by putting x1, whatever the value of x is at this point, we put that into the function. So y at that point, the y value at that point, is function f of x1. That's how we get the radius. Now let's think about all of this, that the height is represented by dx. The radius is represented by function f of x, but we need the radius squared. That's what we need, that's the important thing, radius squared. So that means in our formula to find the volume of this shape, we will have the volume is equal to the integral, and let's say the limits are from a, we'll do it from here actually, from a, x equals a, up to x equals b. Okay, so we've got those 2 points there. We're going from x equals a up to x equals b, and it's going to be pi times the radius squared, which is function f of x squared, times the height, which is dx. So the volume is equal to the integral, the limits of a to b, of pi times the function squared dx. And actually, usually we would write this, remember how I've said pi is just a constant, and I've said that you take the constant outside of the integral sign, and it just simplifies things a little bit for us. So it can be written like this, that the volume is equal to pi times the integration of function f of x squared with the limits from a to b with respect to x. And that ultimately is the formula that we're going to be using to find the volumes of rotation. That's what they're called, volumes of rotation, because we take a function and we rotate it about the x-axis.